Imagine a star. A star many times bigger than our own sun. It lives for millions of years, burning brightly in the cosmic darkness. But eventually, its fuel runs out. The star collapses under its own immense weight. It falls in on itself, squeezing all of its matter into a point of infinite density. This catastrophic event gives birth to one of the most extreme objects in the universe, a black hole. It is a region of spacetime where gravity is so strong that nothing, not even light, can escape its grasp. It is a one-way trip to a destination we cannot comprehend. Our laws of physics break down at its center, a place we call the singularity. To our eyes, a black hole is a sphere of perfect blackness set against the backdrop of stars. It is the ultimate shadow. But it is not always alone. Often, a black hole is surrounded by a swirling, superheated disk of gas, dust, and the shredded remains of unfortunate stars that strayed too close. This is called an accretion disk. The material in this disk spins at incredible speeds, rubbing together and glowing with brilliant, intense light. This halo of fire makes the unseen darkness at its center all the more profound. It is a cosmic lighthouse, signaling the presence of an invisible monster lurking in the void. The sheer power of a black hole is difficult to put into words. Its gravity doesn't just pull on things, it fundamentally changes the space around it. Think of space-time as a flat, stretchy fabric. A massive object like a star would create a small dimple. A black hole, however, creates a bottomless well. Time itself behaves differently near a black hole. For an observer watching from a safe distance, a clock falling toward the event horizon, the point of no return, would appear to slow down, eventually seeming to freeze forever at the edge, even as it plunges into oblivion. This warping of space-time is what makes black holes so mysterious and captivating. They are laboratories where the rules of the universe are pushed to their absolute limits. They challenge our understanding of space, of time, of gravity itself. We cannot see inside them. We can only study their effects on the cosmos around them, the stars they orbit, the light they bend, and the powerful jets of energy they sometimes shoot out into space. They are cosmic enigmas, holding secrets about the very fabric of reality, waiting for us to uncover them from a safe, cosmic distance. Black holes are not always solitary wanderers. In the vast and dynamic universe, galaxies collide, and star systems are born and die together. It is in these crowded cosmic neighborhoods that two black holes can find each other. They might have been born from a pair of massive stars that lived their lives as partners, or perhaps one captured another as their host galaxies merged. Once they are caught in each other's gravitational embrace, they cannot escape. They begin a slow, majestic, and inescapable dance, a gravitational waltz that can last for millions or even billions of years. At first they circle each other from a great distance, like cosmic partners sizing each other up. Their orbits are wide and slow, but with every pass they radiate energy away into space, not as light but as invisible ripples in the fabric of space-time itself. These are gravitational waves. This constant loss of energy causes their orbits to shrink. Ever so slowly they draw closer. The dance begins to quicken. What started as a slow, graceful orbit over millions of years begins to accelerate, setting the stage for a truly spectacular and violent finale. The cosmic stage is set for a performance of unimaginable power. As the two black holes spiral inward, their immense gravity begins to dramatically warp the space around them. Light from distant stars that passes nearby is bent and distorted, a phenomenon called gravitational lensing. An observer would see the background of stars swirl and magnify, creating strange, ghostly rings and arcs of light. It would look as if the universe were being viewed through a warped, cosmic magnifying glass. The accretion disks of gas and dust surrounding each black hole would glow even brighter, agitated by the intense tidal forces, painting the scene with chaotic and brilliant colors. The closer they get, the more extreme these effects become. The two swirling accretion disks can merge, forming a massive, turbulent river of superheated gas that flows between the two dark abysses. This shared disk of matter glows with unimaginable intensity, a final brilliant flare before the inevitable end. Stars and planets that were once in stable orbits are thrown into chaos. Some are flung out into interstellar space at incredible speeds, while others are pulled into the swirling vortex, their matter torn apart and added to the glowing chaos. The dance is no longer graceful, it has become a frantic, spiraling frenzy. In the final moments of their long dance, the two black holes are moving at a significant fraction of the speed of light. They are now so close that they orbit each other several times every second. Space-time itself is being twisted and distorted like a storm-tossed sea. The universe holds its breath. The immense gravitational forces at play are beyond anything we can replicate or fully comprehend. The light from their shared accretion disk is a final, desperate scream before the two singularities, the 2 points of infinite density, finally touch. This is the point of no return for the black holes themselves. The collision is not a crash in the way we might imagine two solid objects hitting each other. Instead, the two event horizons, the two spheres of blackness, touch, tremble, and merge. In that instant, they become one. The resulting newly formed black hole is a distorted, quivering object. It is temporarily shaped like a peanut or a misshapen teardrop, vibrating violently from the force of the merger. It quickly shakes and wobbles, trying to settle into a stable spherical shape. This process, known as ringdown, is like a bell being struck, but instead of sound, it radiates powerful gravitational waves. This merger unleashes a burst of energy that is almost beyond belief. For a fraction of a second, the collision radiates more power than all of the stars in the observable universe combined. But this energy is not released as light, heat, or sound. It is released purely as gravitational waves. These are powerful ripples in the fabric of space-time itself, expanding outward from the collision at the speed of light. The cosmic sea is rocked by a tidal wave of gravitational energy generated by the most violent event the universe has to offer since the Big Bang. The aftermath is a scene of transformed space. Where there were once two black holes, there is now a single, larger, more massive black hole. It is quieter now, its ring-down vibrations fading as it settles into a perfect sphere. It is slightly smaller than the sum of the two original black holes because a tremendous amount of their mass, sometimes equivalent to several suns, was converted directly into the energy of the gravitational waves. The surrounding space is forever changed, and a new, more massive gravitational anchor now sits at the heart of what was once a cosmic dance floor. Those ripples in space-time, the gravitational waves, travel across the universe unimpeded. They pass through stars, planets, and galaxies as if they were nothing. They carry with them the story of their cataclysmic birth, the masses of the two black holes, the speed of their final spiral, the violence of their merger. For billions of years, these echoes travel through the cosmic dark, growing fainter as they expand across unimaginable distances. They are a message from a distant past, a ghost of a cosmic collision that happened long ago in a galaxy far, far away. And here on Earth we have built instruments sensitive enough to feel these faint tremors. Observatories like LIGO and Virgo are giant detectors designed to sense a distortion in space-time smaller than the width of an atomic nucleus. When a gravitational wave from a distant black hole collision passes through our planet, it stretches and squeezes everything, including the detectors themselves. On September 14, 2015, we felt it for the first time. We heard the chirp of two black holes spiraling into each other, a sound that confirmed one of Einstein's most profound predictions and opened a new window to the cosmos. Why is this so exciting? Because it gives us a new way to see the universe. For all of human history, we have studied the cosmos using light, visible light, radio waves, X-rays, but many of the universe's most dramatic events, like the collision of two black holes, happen in complete darkness. Gravitational waves allow us to listen to the universe's hidden symphony. They let us observe the unseeable. Each detection is a chance to test the limits of our understanding of gravity and to witness the life cycle of the most extreme objects in existence. These cosmic collisions are more than just a scientific curiosity. They speak to something deep within us, our sense of wonder and our place in the universe. They remind us that the cosmos is a dynamic, evolving, and sometimes violent place, but it is also a place governed by elegant and powerful laws. By listening to the echoes of these ancient epic events, we are not just collecting data, we are connecting with the grand, ongoing story of the cosmos. We are looking into the heart of creation and destruction, and in doing so we learn a little more about the magnificent universe we call home.